You think you're watching this video, but according to the laws that govern reality, you're simultaneously watching it and not watching it. The photons hitting your eyes exist in multiple states until the exact moment your brain processes them. Even more bizarre, your act of watching is literally creating the reality you're experiencing. Sound impossible? Einstein thought so too. He spent the last 30 years of his life trying to prove this was wrong. He failed, and the reason he failed will shatter everything you think you know about existence. I'll show you why the universe is far stranger than science fiction, why your common sense is completely useless at understanding reality, and why the deepest truth about existence might be that there is no truth, only observations creating reality moment by moment. The quantum coin flip. Let's start with something impossible. Imagine you have a coin that doesn't follow normal rules. When you flip this quantum coin, it doesn't land heads or tails, it lands both simultaneously. The coin exists in what physicists call a superposition of states. But here's where it gets really weird. The moment you look at the coin to see which side it landed on, reality makes a choice. The coin suddenly decides to be either heads or tails. Before you looked, it was genuinely both. After you looked, it's definitely one. This isn't just a thought experiment. This is exactly how the fundamental particles that make up your body behave every single moment. Electrons around atoms don't orbit like tiny planets. They exist as probability clouds, simultaneously occupying multiple positions until something forces them to choose. Werner Heisenberg, one of the founders of quantum mechanics, discovered that this uncertainty isn't just about our inability to measure precisely. The uncertainty is built into the fabric of reality itself. An electron doesn't have a definite position and momentum at the same time, not because we can't measure both, but because both don't exist simultaneously. This principle, known as the Heisenberg uncertainty principle, suggests that at the quantum level, the universe is fundamentally probabilistic, not deterministic. Every quantum interaction is like rolling dice, where the outcome is genuinely random, not just unpredictable. If this is blowing your mind already, hit that like button, because we're just getting started, and what comes next will make this seem simple. The observer effect and measurement problem. Now here's where quantum mechanics gets philosophically disturbing. What counts as observation? Does it require a conscious mind? Or is any measurement device enough to collapse the wave function? In the early days of quantum mechanics, some physicists proposed that consciousness itself played a fundamental role in determining reality. This led to interpretations suggesting that the universe remains in an indefinite state until a conscious observer makes a measurement. But modern physics has moved away from this idea. We now understand that any interaction with the environment, whether it's a detector, a photon, or even air molecules, can cause what we call decoherence. The quantum system becomes entangled with its surroundings, effectively making a measurement. This is why don't see everyday objects in quantum superposition. A basketball isn't simultaneously on the court and in the stands because it's constantly interacting with air molecules, light, and gravity. These interactions force it into a definite state. Yet, the mystery remains. Why does measurement cause this collapse? This is called the measurement problem, and after nearly a century of quantum mechanics, we still don't have a complete answer. Some physicists propose that collapse never actually happens. Instead, every possible outcome occurs in parallel universes. Others suggest that particles have definite properties all along, guided by hidden variables we can't detect. Each interpretation paints a radically different picture of reality. The building blocks of everything. Let's zoom into the smallest scales imaginable. Everything you see, your hand, this screen, the air you breathe, is made of atoms. But atoms aren't solid little balls. They're mostly empty space with a tiny nucleus surrounded by probability clouds of electrons. The nucleus itself is made of protons and neutrons, which are composed of even smaller particles called quarks. These quarks have bizarre properties. They have color charge, though not actual color, and they're held together by particles called gluons that get stronger when you try to pull quarks apart. But here's the truly mind-bending part. These particles aren't really particles at all. They're excitations in quantum fields that permeate all of space. Think of reality as an infinite ocean, and what we call particles are just waves on that ocean surface. The electromagnetic field fills every point in space. When it gets excited enough, we observe a photon. The electron field is everywhere too. When it vibrates, we see an electron. There are fields for every fundamental particle, all overlapping and interacting in complex ways. This means that even in empty space, these fields are still there, constantly fluctuating at the quantum level. Virtual particles pop in and out of existence, borrowing energy from the vacuum itself and paying it back so quickly that they can't be directly observed. These virtual particles aren't just theoretical curiosities. They have measurable effects. They slightly shift the energy levels of atoms. They create a tiny force between uncharged metal plates in a vacuum, and they might even be responsible for the mysterious dark energy driving the universe's expansion. Quantum entanglement, the universe's strangest connection. Now let's talk about the phenomenon that made Einstein so uncomfortable he spent years trying to disprove it: quantum entanglement. When two particles become entangled, they remain connected in a way that defies our understanding of space and time. Measure one particle and find it spinning clockwise, and instantly, faster than light could travel between them, the other particle will be spinning counterclockwise, no matter how far apart they are. Einstein called this spooky action at a distance because it seemed to violate the speed of light limit. He believed that particles must have predetermined properties, like coins that are already heads or tails before you flip them. He thought quantum mechanics was incomplete. There must be hidden variables determining the outcomes. But in 1964, physicist John Bell proved that Einstein was wrong. Bell's theorem shows that no theory based on local hidden variables can reproduce all the predictions of quantum mechanics. The universe really is non-local. Particles can instantaneously influence each other across vast distances. This has been confirmed in countless experiments. Photons entangled in laboratories have maintained their mysterious connection across continents. Scientists have even achieved quantum teleportation, not of objects, but of quantum states, instantly transferring the complete information of one particle to another. This non-locality doesn't violate relativity because you can't use entanglement to send information faster than light. The correlations are perfect, but they're random. It's like having two magic coins that always land opposite to each other. You can't control which way your coin lands, so you can't send a message. But the implications are staggering. Entanglement suggests that the universe is fundamentally interconnected in ways we're only beginning to understand. Some physicists propose that space itself emerges from entanglement between quantum fields. Schrödinger's cat and the quantum-to-classical transition, Erwin Schrödinger, was troubled by the implications of quantum mechanics. So he devised a thought experiment to highlight what he saw as its absurdity. He imagined a cat in a box with a device that had a 50% chance of releasing poison based on a quantum event, like the decay of a radioactive atom. According to quantum mechanics, before you open the box, the atom exists in a superposition of decayed and not decayed states. This means the cat should be in a superposition of dead and alive states. Schrödinger thought this was ridiculous. Cats are either alive or dead, not some bizarre combination of both. But Schrödinger's intuition was wrong. Modern physics has created actual Schrödinger cat states with larger and larger objects. Scientists have put individual atoms, then molecules, then tiny crystals into quantum superposition. The current record holders involve objects with billions of atoms. So why don't we see everyday objects in superposition? The answer is decoherence. Large objects interact with their environment in countless ways. They emit heat radiation. They bump into air molecules. They respond to gravitational fields. Each interaction entangles the object with its surroundings, effectively measuring it and destroying the superposition. The boundary between quantum and classical behavior isn't sharp. It's determined by how well an object is isolated from its environment. In carefully controlled laboratory conditions, we can maintain quantum coherence in surprisingly large systems. Some researchers believe we might eventually observe quantum effects in objects visible to the naked eye. This raises profound questions about the nature of reality. Are there truly quantum effects happening in your brain? Some controversial theories suggest that consciousness itself might depend on quantum processes in neural microtubules, though most neuroscientists are skeptical. The many interpretations of quantum reality. After nearly a century, physicists still can't agree on what quantum mechanics actually means. There are dozens of interpretations, each painting a different picture of reality. The Copenhagen interpretation, favored by many physicists, says we should stop asking what's really happening and focus on what we can measure. Wave functions collapse upon measurement, but the interpretation remains agnostic about why or how this happens. The many worlds interpretation takes the mathematics of quantum mechanics completely seriously. It says wave functions never collapse. Instead, every possible outcome of every quantum event actually occurs in parallel universes. Right now, there are countless versions of you in universes where different quantum events played out differently. This sounds crazy, but it's mathematically elegant. There's no special role for measurement, no mysterious collapse, just the smooth evolution of a universal wave function that branches into multiple realities. De Broglie-Bohm theory maintains that particles always have definite positions and velocities, but they're guided by a pilot wave that creates quantum behavior. This interpretation is deterministic and realistic, but it requires faster-than-light influences and is generally considered less elegant. Quantum Bayesianism, or Cubeism, suggests that quantum states represent our knowledge about systems, not the systems themselves. Wave functions are subjective, describing what an observer can predict about future measurements. Each interpretation makes identical predictions for experiments. They're empirically equivalent. This frustrates many physicists who want quantum mechanics to give us insight into the nature of reality, not just computational tools for making predictions. Quantum fields and the fabric of space-time. Let's go deeper into what might be the most fundamental level of reality: quantum fields. These aren't just mathematical abstractions. They appear to be the true substance of the universe. Every fundamental particle corresponds to a field that fills all of space. The Higgs field gives particles mass. The electromagnetic field carries light and electromagnetic forces. The strong nuclear field holds atomic nuclei together. The weak nuclear field governs certain types of radioactive decay. These fields are constantly fluctuating at the quantum level, even in empty space. The vacuum isn't truly empty. It's a seething foam of virtual particles popping in and out of existence. These fluctuations have real measurable effects on the universe. Some theorists propose that space and time themselves emerge from the entanglement structure of quantum fields. At the deepest level, there might not be points in space or moments in time, just patterns of quantum information that give rise to the space-time we experience. This connects to one of the biggest mysteries in physics, the relationship between quantum mechanics and gravity. Einstein's general relativity describes gravity as the curvature of space-time, but we don't yet understand how to reconcile this with quantum field theory. String theory attempts to unify these frameworks by proposing that fundamental particles are tiny, vibrating strings rather than point particles. In string theory, the different vibrational modes correspond to different particles, and gravity emerges naturally from the theory. But string theory remains highly speculative, with no experimental confirmation. Alternative approaches like loop quantum gravity suggest that space itself is quantized, made of discrete units at the smallest scales, like pixels on a cosmic screen. Quantum technology and future applications. Quantum mechanics isn't just abstract philosophy, it's the foundation of modern technology. Lasers, transistors, MRI machines, and GPS satellites all depend on quantum effects. But we're now entering a new era of quantum technology that promises even more revolutionary applications. Quantum computers use superposition and entanglement to perform certain calculations exponentially faster than classical computers. Instead of bits that are either 0 or 1, quantum computers use qubits that can be 0, 1, or both simultaneously. This parallelism allows quantum computers to explore multiple solutions to problems simultaneously. They could break current encryption methods, simulate quantum systems for drug discovery, and solve optimization problems that are intractable for classical computers. We're also developing quantum communication networks that use entanglement to create unbreakable encryption. Any attempt to intercept a quantum encrypted message necessarily disturbs the quantum states, alerting the communicators to the presence of an eavesdropper. Quantum sensors can detect tiny changes in gravitational fields, magnetic fields, and time itself. They might help us discover dark matter, detect gravitational waves from the early universe, or even test the foundations of physics in previously impossible ways. But perhaps the most profound impact of quantum technology will be on our understanding of reality itself. As we build larger quantum computers and more sophisticated quantum experiments, we might finally answer some of the deepest questions about the nature of existence. The information revolution in physics. Some of the most exciting developments in modern physics come from thinking about quantum mechanics in terms of information. This perspective suggests that information, not matter or energy, might be the most fundamental aspect of reality. In quantum mechanics, the act of measurement doesn't just reveal pre-existing information, it appears to create information. When a quantum system is in superposition, there's literally no fact of the matter about which state it's in. The information about its definite state doesn't exist until a measurement forces it into being. This has led some physicists to propose that the universe is fundamentally computational. Reality might be like a vast quantum computer, processing information and computing its own future states. In this view, what we call physical laws are actually algorithms running on cosmic hardware. The holographic principle emerging from black hole physics suggests that all the information in a volume of space can be encoded on its boundary. This implies that our three-dimensional reality might be a projection from information stored on a two-dimensional surface, like a hologram. Quantum error correction, developed for quantum computing, might also explain why we observe classical reality, despite living in a quantum universe. The environment acts like a quantum error correcting code, suppressing quantum fluctuations and maintaining stable classical information. These ideas are still highly speculative, but they represent a shift toward thinking about physics in terms of information processing rather than mechanical interactions. The universe might be less like a machine and more like a mind. The limits of knowledge and the future of physics. As we push deeper into quantum reality, we encounter fundamental limits to what we can know. The uncertainty principle isn't just about measurement precision. It might reflect deep limitations on the concept of objective reality itself. Some interpretations of quantum mechanics suggest that there simply isn't a complete description of reality that's independent of observers. The universe might be irreducibly relational. Properties exist only in the context of interactions, not as absolute features of objects. This connects to ancient philosophical questions about the nature of existence. If reality is fundamentally quantum, then perhaps the Buddhist concept of interdependence, that all phenomena exist only in relation to other phenomena, is literally true at the physical level. We're also approaching technological limits that might reveal new physics. As computer chips get smaller, they're beginning to exhibit quantum effects that interfere with classical computation. As our measuring devices become more precise, they're bumping up against quantum noise that can't be eliminated. The next generation of experiments might finally distinguish between different interpretations of quantum mechanics. Tests of quantum gravity effects, observations of quantum behavior in biological systems, and exploration of the quantum to classical transition could reshape our understanding of reality. But there's also the possibility that some questions simply can't be answered. The universe might be stranger than we can imagine, operating according to principles that transcend human comprehension. Our brains evolved to navigate a classical world. There's no guarantee they're equipped to understand quantum reality. We've journeyed from the everyday world of common sense to the bizarre realm of quantum mechanics, where particles exist in multiple states simultaneously, where observation changes reality, and where distant objects remain mysteriously connected. This isn't just abstract physics. It's the foundation of everything you see and experience. Every atom in your body, every photon hitting your eyes, every chemical reaction in your brain operates according to quantum principles. The quantum world reveals that reality is far stranger and more wonderful than our ancestors could have imagined. It challenges our most basic assumptions about existence, causality, and the nature of information itself. As we continue to explore this quantum frontier, we're not just learning about particles and fields, we're discovering what it means to exist in a universe where the impossible is routine, where mystery is built into the very fabric of reality. The next time you look around, remember, you're not just observing reality. In some deep quantum sense, you're participating in its creation. The universe is far more magical than we ever dared to dream. If this journey into quantum reality fascinated you, make sure to subscribe and hit the notification bell, because we're diving into even stranger territories next week. I want to hear your thoughts. Does this change how you see reality? Drop a comment below and let's discuss what it means to exist in a quantum universe. Thanks for joining me on this journey into the quantum realm. The mystery continues, and the adventure is just beginning.